Welcome to Chapter 6, Recitation. This chapter is talking about thermochemistry. You need to refer, just a little thing for this chapter, you're going to need to refer, you don't have to memorize it, but you need to refer to table 6.4 on page 257. It is about specific heats. We'll talk about specific heats. It's the amount of heat capacity, grams required to raise 1 gram. Actually, it's in joules. It's the amount of heat in joules required to raise 1 gram of substance, 1 degree of water. 1 gram of substance, the temperature of water by 1 degree Celsius. And so like a water, specific heat capacity is 4.18, and that's joules per gram degrees Celsius. Copper is 0.385 joules per gram degrees Celsius. So you need to understand that, you see the difference in these numbers, the whole number 4 versus 0.3. Basically, this tells you a little bit about the substance, about how quickly and how not so quickly that these substances hold and retain the heat. So water, it takes a long time for the water to absorb heat, and then it takes a long time for the water to cool down, as opposed to copper. That's why you have a lot of copper that lines your pans when you want to boil water. Okay, so understand what those heat capacities mean. We'll also talk about equations like Q, which is the heat capacity, times mass, times specific heat, times the change of temperature. But a lot of times what I do when I want to know what my units are, I look at the constants that are given to me. So our specific heat units are joules per gram per degree Celsius, and so I let that kind of lead me with my units. Also, something that's discussed in the lecture videos is state functions. So your state functions are delta E for energy, delta P for pressure, delta V for volume, and delta T for temperature. And these all mean that you can basically take like the final temperature minus the initial temperature. That's what the delta means. So that's equation yourself. They're capital letters. So anytime you need to do a delta E or a delta P or delta V or delta T, it's the final minus the initial. And so that should help you memorize those formulas. And the other formulas in this chapter are W equals negative P delta V. So you got two state functions there. You got pressure and change of volume. You also need to know the conversion factor 0, 101.3 joules equals 1 liter times atmosphere. So you'll need to use that conversion. And I think we're probably ready to begin. So, what I always like to tell you on this slide is what problems to submit for recitation. So I want problems 6.2, 6.4, 6.6, and 6.7. So those are the 4 problems to submit for your recitation participation points. Okay, the first problem we'll work is 6.1. And even though I didn't put this as one of the problems you submit, it's an important problem because it tells you how to use the delta H delta H, the enthalpy for reaction. So page 265 in your book talks about enthalpy, and this is basically how much heat's given off. Now, at constant pressure, and constant pressure is like 1 atmosphere, like what we're in. So a lot of reactions that you do, you're doing at constant pressure. It's not often you're changing the pressure. So what's interesting, and you need to know this for the exam, is delta H equals the heat in a reaction. And that little p, subscript p, that means constant pressure. So when you're doing reactions at 1 atmosphere, they're open systems. You can, if you can measure your heat, that's also the same as your change in enthalpy. That's kind of nice too, because if you notice, the delta H, the capital letter H, also makes that a state function. Remember the delta H, final minus initial. Work is not work, but work isn't, but also Q, the heat, the little Q, the heat of reaction, which is always measured in joules, is not a state function. So it does depend on its path. So in this one, this problem, you're going to want to convert the grams to moles. Because when we're dealing with a reaction, and we're dealing with delta H of a reaction, we work in moles. So the problem gives us 0.834 grams of sodium. So we need to get that to moles. And so if you look at the molar mass on your periodic table, you'll see basically 23 grams of sodium is equivalent to 1 mole of sodium, and that gives you 0.0363 mole of sodium. You've got to get it in terms of moles. So when you add 0.0363 mole of sodium to an excess of hydrochloric acid, you find that 8,670 joules of heat are produced. Okay, so if it's produced, what is that? That is an exothermic reaction, so it's delta H for this reaction, 8,670 joules. What is the enthalpy of the reaction is written below. So we've got to get this in terms of moles. So the way that I did this reaction was 0.0363 mole of sodium, and you see the superscript here, or superscript coefficient, for 2 mole of sodium we get negative 8,670 joules, and that works out to negative 157.2 joules. And that is the enthalpy of the reaction is written below. I noticed in this problem set, we didn't have a lot of reactions using the delta H of the reaction as a conversion factor. I would practice a few of those because you will see that on the exam. So, and you have problems for that in the book. So look at Tro. This is problem 6-2, and this is important because it talks about the heat capacity and specific heat. So the temperature of an object increases by 29 degrees Celsius when it absorbs 3,693 joules of heat. Okay, so when it's increasing by 29 degrees, it's already telling you that the delta T is 29.0 degrees Celsius. Now, your equation here is Q equals heat capacity times the change of temperature. And so then we just put in, you plug and check, 3,693 joules of heat equals C times 29.0 degrees Celsius. You divide both sides by 29.0 degrees Celsius. ends up equaling out to 127.3 joules per gram degrees Celsius. What is heat capacity? Heat capacity is C of the system as the heat is required to change the temperature by 1 degree C. Now, the heat capacity is characteristic. That means it can be used to identify an object. So, and this is how you could use it in such a way. The mass of the object is 331 grams. Use the table of specific heat to identify the object. Well, what you want to do here is you want to put into the formula, and this is going to be this equation, Q equals, because this is specific heat, which is the CS, you have to take the mass times CS times delta T, and delta T equals 29.0 degrees Celsius. Our Q, our heat, equals 3,693 joules. And then here, if we take the mass is given to us 331 grams. Now, so you know what units you need everything in, and make sure your units are correct. I usually use, you're not going to have to memorize specific heats, they would always be given to you, but I look at whatever the constant or is in an equation. So we do have Q in joules, we do have our delta T in degrees Celsius, and we do have our mass in grams. So this is going to work out. So we just plug and chug at this point. And so we would write 3,693 joules equals 331 grams times CS times 29.0 degrees Celsius. And when you multiply and divide through, you get CS equals 0.385. And that would end up being joules per gram per degree Celsius. And that is copper right there. The next problem is problem 6-3. Heat capacity and specific heat again. How do you know these things? Okay, well, when you're reading it, if you weren't given the title here, liquid sodium is being considered an engine coolant. How many grams of liquid sodium are needed to absorb? So we got Q here. Absorb 7.00 megajoules. So we're going to have to convert that to joules using our SI unit, our table. You hopefully already have memorized 1.2 on page 17. We want to work out the units. When they also say absorb, this is going to be a endothermic reaction. Therefore, it's going to be a positive J. So work on anytime you can process that, it's good practice, whether you actually was asking for it or not. So, in the form of heat, so that's Q, in the form of heat is Q, if the temperature of the sodium is not to increase more than 10 degrees Celsius, so let's just go ahead and put delta T, we'll put equals 10.0 degrees Celsius. So we're given a delta T, we're given a Q, and they want how many grams. So right off the bat, you should recognize that you're given these certain units that can solve for this equation here, right? The heat equals mass times specific heat times delta T. And let's go ahead and convert the 7.00 megajoules into joules. Mega is bigger than the base unit, and it's 6 zeros. So big number is going to go with the smaller unit. So there are 100 100,000 joules in 1 megajoule. This is going to be 760 joules. That's a lot of heat. And we can put that in there for Q. We're going to be solving for what? Grams. So we're going to be solving for mass. Where do we get our specific heat? CS. You need to look at the table or the appendix. Table. Oh, they give it to you right here. CP. Not sure why that's P, but maybe it's a different pressure. So 30.8 joules per Kelvin per mole. Okay, notice it's in Kelvin. And what did I say? Whatever this is, you just convert to it. So you're going to write this in, 30.8. This is joules per Kelvin times mole. And then our delta T is right here. And because this is Kelvin, I'm going to go ahead and convert that to Kelvin. So you add 273 on that, and that would be 283 Kelvin. Now when you solve this, you multiply 283 times 30.8 and divide both sides. And that number you should get 803.08 mole. Because the units are going to cancel out. Joules will cancel out, Kelvin will cancel out, and you're going to be left with mole. Now, what's the question? It asks for how many grams. Well, you know how to go from mole. You can go from 803.08 mole of sodium. And you look at the molar mass, mole of sodium, 23.00 grams of sodium. And that should be 1.85 times 10 to the 4th grams of sodium liquid is the answer. This is problem 6-4. A sample of gas occupies a volume of 69.8 milliliters. As it expands, okay, when it expands, let me just point these words out, okay, it means it does work on the surrounding. Okay, so it loses energy, it lost energy because it did work. So that's always going to be negative. So just associate expansion of a gas with negative work. Okay, what is our equation for work? We're talking about work. We're talking about gas expanding. You have to have this memorized. Work equals negative P delta V. Work is not a state function, but P delta V are. Here's page 261. So now we define it. The initial volume is 69.8 milliliters. And it expands. And the work, so what's the work going to be? It's going to be negative 116.9 joules. Because 116.9 joules of work on its surroundings at a constant pressure. Okay, so the pressure is not changing, it's staying constant, and it's at 783 torr. Now when you get torr, you need to convert torr into atmosphere. So you should have memorized from last chapter that 1 atmosphere equals 760 torr. So we can convert 783 torr that by 760 torr for 1 atmosphere. And that works out to be 1.03 atmosphere. So in order to do this equation, you also need to memorize 101.3 joules equals 1 liter times atmosphere. You have to memorize that, and because you want all your units to be the same. So what you want to do here is, since we're putting our change of volume in atmosphere, and we're going to have to convert this to liters. So we got VI, our initial volume, and 69.8 milliliters, 1,000 milliliters in 1 liter. So that works out to be right here, 0.0698 liters. And that's your initial volume. And they want to know the final volume. What is the final volume of the gas? So you also want to convert work into liters atmosphere. So we're going to go to negative 116.9 joules. And we have 101.3 joules equals 1 liter atmosphere. And that's going to be 1.15 liters per negative atmosphere. Now you have everything in the right units. You can just plug and chug into this formula here and solve for your final volume. So let's rewrite this. Work equals negative P, and delta V is V of the final minus V of the initial. So your work is negative 1.15 liters times atmosphere. You're at a constant pressure. We converted the torr to atmosphere, so it's negative 1.03 atmospheres. We're going to solve for VF, and we're going to subtract the V initial, and we have that in liters. That's 0.0698 liters. So you want to multiply this through, and that'll work out to be, multiply this by VF, and you take, I'll do that real quick for you, negative 1.03 times negative 0.0698. So this ends up being negative 1.15 liters times atmosphere equals negative 1.03 atmosphere VF plus the negative times a negative 0.071196. That's liters times atmosphere. This is addition. You're going to subtract this from both sides of the equation. And remember, they have the same units. That's why we took the time to do that. And so negative 1.15 minus negative 0.0, negative 1.15 minus 0.071196 equals negative 1.221196. We round at the end, liters times atmosphere, equals a negative 1.03 atmospheres times VF. We divide both sides by negative 1.03 atmospheres, divided by negative 1.03 atmospheres, and our final volume then would be positive 1.1856. Your atmospheres cancel out, you're left with liters. That's good because that's what you want with the volume. And we round this to 3 significant figures. 1.19 liters is your final volume. Is that larger than your initial volume? Is your initial volume? Yes, and it expands, so it makes sense. This is problem 6.5. 6.5 is talking about pressure and work again, and I can't stress this enough. I'm going to go ahead and stress it again. When you see expansion, I want you to think of negative work. When you see compression, that is positive work. You're talking about the system compared to the surroundings. Now, the other thing I want to tell you, it's only the gases that expand. Solids don't expand in a reaction. Liquids don't expand, okay? It's gases. So, that's why I was talking about gas expansion, and we're going to have another problem later on talking about expansion of gas. So, just make sure you're focused on these things. Okay, the first part is basically telling you what the initial volume is. Initial volume is defined at 1.00 liters. And this question wants you to calculate the work if the gas expands against the constant internal pressure of P equals 1.00 atmospheres to a final volume, so VF equals 10.0 liters. So what's our formula that we memorize? Work equals negative P delta V. And if we put negative 1.00 atmospheres in here, and we do VF minus VI, that's basically 10.0 liters minus the 1.0 liters, and that works out to be 9. The answer to this problem then ends up being a negative 9.00 liters times atmospheres, and we don't want it in liters times atmosphere, so we're going to have to convert, because work needs to be in joules. So for this problem, number one, you need to convert the negative 9.00 liters times atmosphere using our conversion of 1 liter times atmosphere equals 101.3 joules. And that works out to be negative 911.7 joules. Now, the point of this problem is to show you that the total amount of work is not independent of the path taken. So, if a gas expands from 1 liter to 10 liters, and it just does it straight up, you see that it gives off, it does 911.7 joules of work. However, if you go to the second part of this problem, it's carried out in 2 steps. And what we're going to do is we're going to calculate step 1 and then step 2 of what the work is using the same formula. Work equals negative P delta V, and then we're going to add these together. So we're going to have work 1 and we're going to have work 2, negative P delta V. And then we're going to have the total work, and this total work is going to be work 1 plus work 2. And what you're going to see is that this is actually a larger number than the first problem, and that's because it is dependent on the path. Just like, think about it. If you work up a hill and you go zigzag up that hill, and your friend goes straight up the hill, who does more work? In theory, over the distance, you've probably done more work if you've done zigzag. Okay, so let's just look at this. Let the gas expand. Remember the initial, once again, still the 1.00 liters in the very beginning. So let's look at work 1. It's showing you that the external pressure is 5, so negative 5.00 atmospheres, times VF, which is a volume of 2.00 liters, minus the 1.00 liters. And if you multiply this through, you should get, not too hard is it, negative 5.00 atmosphere liter. And then let's go ahead, the proper unit, people like to speak for work is in joules. We need to convert that liter atmosphere using the conversion. 1 liter atmosphere equals 101.3 joules. And that should work out to be negative 5.06.5 joules for work 1. Now work number 2. Work number 2, same formula, but the external pressure is now 1 atmosphere, and we went from 10 liters, let the gas expand to 10 liters. So where are we at? We're at 2. Okay, so times that on that. So that's minus 2.00 liters, and this will work out to be 8.00 liters times negative 1 is negative 8.00 atmospheres, and we are going to now convert that. So negative 8.00 liter atmosphere over 1. For 1 liter atmosphere, we have 101.3 joules. And what does that equal on our calculator? Negative 8 times 101.3. We get negative 810.4 joules. And if we add work 1 plus work 2, we get negative 1,316.9 joules. And if you compare that with the first problem, where you're just heating it straight up, it's very different. That was negative 911.7 joules. This is gives off 1,316.9 joules. The next problem is problem 6-6. This is the one I was kind of telling you, kind of foreshadowing about gases, and gases are the ones that do the work. So at constant pressure, and you have work, what's your formula? Work equals negative P delta V. When they say constant pressure, go ahead and make that 1.00 atmosphere pressure. That's what we're at, right? And so work equals negative 1.00 atmosphere times V final minus V initial. And basically, it needs, if it does work on the surrounding, which of these do work on the surrounding? They want expansion. Expansion means negative. In order for this to be negative, this whole thing to be negative, this needs to expand. That means the V finals better be larger than the V initial. The only way you're going to get this be negative work because of that negative sign. Otherwise, that's going to be a negative. If V initial is greater than V final, it's going to be a negative quantity, and a negative times the negative would then be positive. So this V final needs to be greater than V initial. And so what you're going to do is you're going to look at the moles of gas in a reaction from your products, and you're going to subtract the moles of gas in your reaction with RXN and your reactants. That's sometimes I've seen these in exams where one of these in parentheses might be a solid, so don't count it. If it's an aqueous or a liquid, don't count it. Only look at the gas molecules. And so basically we're going to do 3 moles of gas, carbon gas, minus, not carbon, it's just gas C, minus how many moles do we have on our reactant side? 4 moles. This is your reactant side. What's 3 minus 4? It's a negative 1. What's a negative 1 times a negative 1.00 atmosphere? That would end up being positive work. And we want work on the surroundings, so we need a negative work. We're looking for negative work. So it's not the first one. Okay, the second one, 3 moles of C gas minus, with our reactant, 3 moles of reactant gas. That equals 0. Well, then your work is going to equal 0. You put it in D, final mark, the initial. The next one, we have 4 moles of the product gas minus 5 moles of your reactant. Once again, that's negative 1, and negative times a negative is going to be a positive work. That's not going to do work on the surroundings. And the last one, we have 4 moles of products of gas minus 3 moles of reactant gas molecules, and that gives you a positive 1. So if you put that in, work equals negative 1.00 atmosphere times some kind of positive number, you're going to get negative work. So this is your answer. And the last problem in this section is problem 6, 7. This is Hess's law. You can find Hess's law on page 271 through 273. When I see all these reactions here, I can now, okay, this is a Hess's law, and we're going to calculate the overall delta H of a reaction. And I always come down here and start with my reaction. So this is my overall reaction, and I just work from left to right. So I look at the first one and I say, okay, 2M. And I find it up here, and I see 2M. And I'm happy because it's solid and it's 2M. It's on the reactant side. I need it to be on the reactant side. This is the equation I'm looking for overall. And it's got the right coefficient in front of it. So at this point, I can check that off, and delta H1 is going to be left alone. I don't have to reverse the sign because I reversed the reaction, and I don't have to divide it or multiply it by a certain number because I don't have to do anything to the reaction. So then I go down here to 3 chlorine gas, and I look up at the 4 reactions, 1, 2, 3, and 4, and I see if I can find chlorine gas. Okay, I have found it. Chlorine gas. And is it on the reactant side? Yes. Okay, so I don't worry about that. So I don't have to reverse the sign of the reaction or reverse the reaction. However, it doesn't have the right coefficient, right? So I'm going to have to multiply a 3 through this equation. I'm going to put 3 hydrogen, a 3 in front of the chlorine, and what's 3 times 2? 6 in front of my chlorine gas. And whatever I do to this, I've got to do to the delta H. So for delta H3, we're going to have to do 3 times negative 1,845.0 kilojoules. So we're going to have to multiply that by 3. And so this is going to end up being plus delta H times 3. And I'm happy because now I've got that, and we're good. And now I go to the last one on the products, and I see NCl3 solid. So I go through reaction 1, 2, 3, and 4, and I try to find NCl3 solid. And I see an NC3L aqueous, that's not it. And then I see it here. This is what I want. but it's on the wrong side of the equation. I need it to be on the other side. So I'm going to rewrite this equation. MCl3 aqueous goes to MCl3 solid. And when I do that, I've got to reverse the sign of this delta H4. It's going to be now a positive 197.0 kilojoules. So it's going to be 197.0 kilojoules to be positive. And what else do I need? Well, I need a 2 in front of there. So I'm going to multiply a 2 through, and then I'm going to take this times 2. So when I do 197.0 times 2, the delta H4 ends up being 394 kilojoules. So now what I'm going to do is I'm going to look at these equations, and I should be good. We'll see. I have to cross out, and hopefully everything cancels out. Everything needs to cancel out. So I'm going to start canceling and crossing out things. So if this is 6Cl hydrochloric acid aqueous on the reactant side, do you see it on the product side? Because if it has the same amount on the reactant side and the same amount on the product side, you can cross them out. This is the only one I see. However, it doesn't have a 6 in front of it, so I'm going to multiply 6 through, and that means I got to do this delta H2 6 times the negative 74.8 kilojoules. Okay, so once I do that, then I can cross out the HCl6 aqueous, and I can cross out the HCl gas, and kind of circle what I have here. So there's that, those are crossed out. MCl3 aqueous, I don't want that. So I'm going to look where I rewrote it here. So now this is the new equation. So that crosses out. Hydrogen gas. 3 hydrogen gas. That's on the product side. This is on the reactant side. So that crosses out. So let's see, we've got these crossed out. There's the 3 chlorine gas. We're going to keep that. That's good. And that's crossed out. And, oh, we didn't even use this. Remember we rewrote this? And there is our 2 MCl3 solid. So everything else crossed out, so it was on both sides of the equation, the correct numbers, and we were left with the overall equation. So now we have to add up all of these delta H's that have been manipulated. So the first one was left alone. So delta H1 is negative 888.0 kilojoules. And then the delta H2 is plus, multiply to 6 through, 6 times negative 74.8 kilojoules. And then we're going to add delta H3. And delta H3, what do we do with that? We took 3 times negative 1,845.0 kilojoules. And then we're going to add our delta H4, which is plus, delta H4 is right here. We went ahead and changed the sign. We switched the product to reactant, and we had to multiply 2 through it, so that ended up being 394 kilojoules. And then you add, and multiply this by 6, multiply this by 3, add these up in your calculator, and your answer should be delta H equals negative 1,400